Okay, so the last, I guess we've had about almost 3 weeks worth of lectures, right? Yeah, so in about 3 weeks worth of lectures, what we have looked at is to understand what we mean by noise in quantum systems. And hopefully I've convinced you that um, the mathematical description of noise or a noise channel for quantum states has this form of a CPTP map, and it has a representation in terms of a finite set of operators in our case, which are called the Krauss operators. So now that we understand the nature of noise and error, the next thing is to discuss what we can do about it, right? So today I want to start by talking about classical error correction. Okay. Because what we do in the quantum case will indeed be motivated by the classical case, but we will see that we simply cannot copy, pun intended, we simply cannot copy what we do in the classical case, right? We'll have to put in a bit more effort to adapt those ideas to the quantum case. So let's just look at a simple noise model in the classical case. So I want to talk about bit flip errors. And we said that these are described by what is often called a binary symmetric channel. And this is what it does. It preserves 0 with the probability 1 minus p and flips it to 1 with probability p. And similarly for the 1 to 0, it's symmetric and it's binary. It's a bit flip channel, right? Like I said, in the classical case, there are not too many error models. Apart from this, you could have something called erasure, right? And everything else can be visualized in terms of these, or these, or pretty much this covers all the so the other, let me just say, the other prominent classical model for errors is that of erasure. Okay, fine. So now what do we do with bit flip errors? I guess the idea is familiar to almost everyone, irrespective of whether you've done a classical error correcting course or not. The idea is that you have to, so to correct for this, so I'm going to be specific and say single bit flip errors. So what do we need to do? We introduce redundancy. So what does that mean? So in place of sending one, you send many, right? And the simplest way to do this is via 3-bit repetition code. So in place of a single 0, you send 3 zeros. In place of a single 1, you send 3 ones. I'm saying send if it's like a communication channel, or if it's a memory, then you store. Or if it's a computation, then you start by doing this process where in the place of a single, you will always put 3 zeros, and in the place of a single 1, you will enter 3 ones. So this idea of going from this, which is the so-called bare bit, in the quantum case, we'll call it the bare qubit, right? This is the unprotected single bit. It is being mapped on to a different space. From the space of a single bit, you've gone to the space of 3 bits. In the classical case, this word space is a bit of a overkill. It's just a field, right? And so this is now a mapping over binary fields, right? And this mapping is what you will call the encoding process. There's not much to it in the classical case. You know what is a string that you are going to input. And you look at that string and you say, if there's a 0, I replace it by 3 zeros. If there's a 1, I replace it by 3 ones. And that's about it. So every bit string, if it is n bit long, right, is going to become, in place of every one of those n bits, I have 3 others. So it will become 3n long, right? So you're going to have something which is 3 times as long. And these two, so let me just introduce some technical terms because we'll often use them in the quantum case as well. And this is a simple way to understand this. So these are what are called code words. Okay. And this mapping is called the encoding. And this new set of strings, right? The 000 and the 111. These are now your new strings. And this constitutes the code. So the code is essentially, in the classical case, a set of these code words, right? And the code words in this case are simply this, the 30 and the 31, right? These are also sometimes called logical 0 and logical 1. Whereas this, in some sense, is the physical bit, right? So you have gone from one single bit to 3 bits, and these 3 bits, this sequence of 3 bits represents a single bit now. So 3 physical bits represent a single logical bit now, right? So the individual entities are your physical bits, and groups of them now represent the logical 0 and the logical 1. So this is what a 3-bit repetition code looks like. Okay. Why is this useful? Why is it useful to send one, 3 in place of 1? So what I've described for you is the first step of an error correcting code. So I often like to show this schematic of an error correction protocol. And the first step in that would be the encoding. And this is what we have done now. We have gone from a single 0, 1 to this, right? So the idea is that, at least when we discuss error correction, we assume that these processes are ideal, right? Which means that until this point, there is no noise. Okay, this encoding has happened in an ideal or noiseless fashion. Okay, so this is of course a crucial assumption, and we'll see much later how we can get rid of this assumption and think about what you can do to your, particularly in the quantum case, what you can do even when these encoding processes, etc., become faulty. Okay, so the next step is when you assume that the noise acts, right? And in this case, it's a single bit flip, right? And after the action of the noise comes error detection and error correction. And often these are lumped together for a good reason, because often once you detect, you immediately know how to correct. Okay, so these are often lumped together, error detection and correction. So this would be the kind of schematic that one has. So now what does, so now let's look at the bit flip noise. So remember, now the noise is acting on the encoded bits. Okay, so we have to understand single bit flip noise on the code words, right? Because now the noise is not acting just on the single bit. You have replaced, every time a single bit has to be stored or sent, you're using 3 bits. So the noise is now acting on all 3 bits. Now comes a crucial assumption about the nature of the noise. And this is true. This is an assumption that we will make, whether classical or quantum. This is always often made. And this is the assumption that the noise is what is called IID. What does IID mean? Have people come across this term? Do people know what this means?
Identically and independently distributed.
Very good. So this says two things about the noise. This says that the noise is identical. Identical means what? It is identical on what? So now that you're talking about noise on multiple bits, the idea is that every bit sees the same kind of noise. It sees the same noise channel. And in particular, it sees the same noise channel with the same noise parameter. What is this noise parameter? This is this P, right? Which is something that lies between 0 and 1. So you either think of this as the probability of a bit flip, and I will often use this interchangeably. I will sometimes say the probability of the bit flip, or more generically, I will just say the noise parameter. So obviously, this is something that quantifies the degree of noise, right? If P is very close to 1, then it's a very noisy channel. If P is very close to 0, then it's not such a noisy channel. It's very close to an ideal transmission or an ideal storage. It's like identity, right? So the value of P tells you the extent to which the bit is corrupted. And when I say identical, it means that every bit is seeing the same identical noise channel with the same noise parameter P. So every bit is seeing the same noise, so same channel and same P. And the second one is the independence. So the noise acts independently on each bit. So the noise, what does this mean? This means that we are essentially ruling out any kind of correlated noise. This is a very strong assumption, right? Well, both are strong assumptions. And in fact, if you try to do stuff on, let's say, an actual physical processor, forget the classical case where our means of realizing classical bits have undergone we've had about 100 years to fine tune how to store and transmit classical information, but we haven't had 100 years to work with quantum bits. So currently, if you look at quantum bits, you will find that both these assumptions break down the minute you look at any simple physical architecture, right? So IBM, will have a 5-qubit processor, which will look, it'll have some such architecture. I think this is one of their standard. This T is one of their standard things, like, something like this. And you will find that if I look at qubit 1, that may behave better than qubit 2, and qubit 3 will be terrible, and qubit 4 will be great, and qubit 5 will be somewhere in between. In the sense, every qubit will have its own decoherence time, right? So really, these 5 qubits are not identical in any way, okay? But the point is, to first order, to a leading order, or to first degree, it turns out that this is a reasonably valid assumption to make, right? So in actuality, yes, you go look at your processors online, and they will say each qubit will come with its own decoherence time and so on. And then you'll be like, what is this IID? IID to first order, okay? Similarly, noise acting independently on every qubit. This again is a very strong assumption. This says that whether or not bit 1 gets flipped is independent of whether bit 2 will get flipped, is independent of whether bit 3 will get flipped, right? So this then means that essentially you're ruling out correlated bit flips in this case. So it is not as if bit 1 flips, there is a higher chance for bit 2 to flip, or there's a lower chance for bit 2 to flip, right? So there is no correlation in the way the noise acts across bits. Another way of talking about it is, if you think of this in some kind of communication scenario where your bits are being physically sent across some channel, when bit 0 is being sent, whether or not bit 0 got flipped has nothing to do with whether or not bit 1 will get flipped. This again is a very strong assumption to make, and obviously one can think of physical scenarios where this will not hold, right? So this is so another way of saying this in the communication context is to say that the channel has no memory. So the channel does not know each bit is being looked at, in a fresh way by the channel. It does not care whether the first bit was flipped or not. It will independently act on the second bit, right? Of course, you can think of scenarios where, depending on when or how each bit is being sent, this can change, obviously, right? And sometimes there can be a bunching effect, which means that bits that are sent very close together will get flipped, whereas a bit that comes much later will see a cleaner channel, and vice versa. So, all of this is only a very first order assumption, right? And to build up a theory of error correction, it is often good to first understand the IID case, and then one can sort of go ahead and look at what happens if these IID assumptions are broken. Okay, so these are very two crucial assumptions captured under this abbreviation of IID, right? And both of these we will assume even in the quantum case. Okay, so what does this give us as far as the bit flip channel is concerned? So now I have these two code words, right? So how does this channel act on these code words? So now you notice that there could be several kinds of errors. So let me list that. So there are different, so what are the possible errors? Because you now have 3 bits, right? So you could have single bit flips. Okay, first of all, you can have no bit flip. You can have single bit flips. You can have 2 bit flips. And you can have a scenario where all 3 bits flip. Okay, right? This is the set of possible errors now. If it's a single bit, then the set of possible errors is just 2, no bit flip and single bit flip, right? But now you have all these other possibilities. Now the question is, what are the probabilities with which these things occur, right? Because now I'm going to think about this P as a noise probability. So then what is the probability with which each of this happens? So let's also write that down. So what is the probability of none of the 3 bits being flipped? I need you guys to answer me in this a little bit. So yeah, what is the probability that no bit is flipped?
1 minus p the whole cube.
Yes, so that is 1 minus p the whole cube. And then what is the probability of the single bit flips? So that is
p into 1 minus p square.
correct. And then 2 bits getting flipped would be p squared times 1 minus p. And then all the 3 getting flipped would be p cubed. Now, of course, there are some prefactors that will come here. And obviously, this is, you can see that this is like a binomial expansion. And there are going to be some prefactors out here. So what is the prefactor before this one? That single bit flip. This can happen in one of 3 ways, right? And the next one, also 3. Yeah. Okay. So this will be the respective probabilities for these things, right? This is the no bit flip. This is the single bit flip. This is the 2 bit flips. And this is the 3 bit flip. Okay. So why is this important? Because now one is looking at orders in P, right? So if you look at the which is the most probable scenario in this, you will notice that if I'm interested in only looking at up to order P terms, then the only things that matter are the no bit flip and the single bit flips. Because anything beyond that is order p squared and higher. Well, in this case, it's only order p cube, but in general, the single bit errors, right, are the ones that will matter. The no error and the single bit error terms are the ones which will be leading order in the probability or in the noise parameter, right? And once again, you assume that you have a good enough physical architecture where this p is going to be quite small. So in the assumption that p is much, much smaller than 1, what will matter really are only the leading order terms, and the leading order terms are the order p terms, right? So let's focus only on those and ask what happens to the 3-bit string. So the 3-bit string gets mapped to 001 or 010 or 100, right? This is what the single bit flips will do. And then of course there is the case that nothing happens to it. So this is the single bit errors. This is what there are 3 possible single bit errors, right? The first, second, or the third, or the most significant, the least significant, and the in-between one. And this is the no flip case. And then similarly, you have your 111. And once again, you have these 3 scenarios with the single bit flip. So this becomes 110, 101, and 011. And once again, these are all your single bit flips. And then you have the 111, which happens if there is no bit flip. So what do you have now? You have a set of 8 strings that the errors have mapped your 3-bit string to, and you notice that these 8 strings are all distinct. So what you have now is a set of 8 distinct 3-bit strings. Indeed, there are only 8 distinct 3-bit strings, and you find that your code, you have chosen your code, although you did this very intuitively and said, okay, in place of 10, I must send multiple zeros. But it turns out that 3 suffices because this 3-bit code word gets mapped to unique, distinct strings under the different sets of errors, right? And that then automatically implies error detection and error correction. So the fact that these are distinct bit strings that every error is mapping this 3-bit strings to implies then error detection is possible. Okay. So of course, like all of this is, so one is only looking up to order P, right? I'm not right now showing what happens to the, when you have 2-bit errors and all that. We'll come to that. Okay. So error detection is possible. So let's look at what we do for error detection. Now, once again, this is all classical, right? So error detection is very simple, right? You just have to check. So you get some 3-bit string at the output, and you simply have to check. What do you have to check? So each of this xi is some 0, 1, okay? And I have a 3-bit string. So what should I check? I have to check which of these 8 strings it is, but what's a better way of saying this? So what do you notice about the ones that the 000 has mapped to and the ones that the 111 has mapped to? So you have basically have to check for parity. So you have to check the parity of the string. What does parity mean? It tells you how many ones, or depends on whether you want to look at it from the ones or the zeros, and then whether that number of ones is even or odd. And you see that if you have an even number of ones, then you should map back to the 111. And if you have an odd number of ones, then you should map back to the 000, right? So the point is, you look at the output string and you can either think of this as a parity check, or you can think of this as a majority voting, right? So if the number of zeros is greater than the number of ones, then you know that this 3-bit string should be mapped to 0, 0, 0. And if the number of ones is greater than the number of zeros, then you know that this has to be mapped to 1, 1, 1. Because you know that at most a single bit has flipped. So depending on how many ones and zeros there are, you map it back to. So this is what the correction step is, right? Similarly, if you do the parity, so let me write again this thing. So, or I'll just mention this here itself. So you notice that all four, okay, so let me write this out here. So 0, 0, 0 gets mapped to either 0, 0, 1 or 0, 1, 0 or 1, 0, 0 or nothing happens. And all of these, so if I count the number of ones as my, if I define the number of ones as my parity, then all of these are odd parity. And if I count, so if I have even parity, okay, sorry, this will not come under that. Wait a minute. So this, of course, has 0 ones, right? Okay. So let me say that I do not include the no error case in this and I only look at this. Okay. So you notice that all of these have even parity. And so by checking the parity, I know, so the point is I first of all detect that an error has occurred. Okay. And secondly, I know which of these, which of the original logical states I should map back to. So whether I should map back to a 0 or a 1 depends on whether this has odd or even parity. So I'm writing this very crudely. Actually, the thing to do, so maybe, I'll discuss that maybe when I do the quantum error correcting code, the same identical code. But actually, if I include the 0, 0, 0 also here, right? Okay, so let me write this out separately. What one can do is not just this simple parity check, but this kind of a parity check where you look at, so you look at the parity of pairs of bits. Okay, so the correct way to go about this, although you notice that there is a parity behavior in the way the error maps, right? So this is the action of the error. The way to do the detection, so let me just discuss this here itself, and then I'll expand on this when we do the quantum version of this. So the way to do the detection is actually to check the parity of pairs of bits in the 3-bit string. So if you look at these pairs, right, from this, you can essentially make out where the error has occurred and what kind of error it is. Okay, so here I'll just leave it with this because my intention is not to discuss the classical 3-bit code. Okay, but I'll discuss this in greater detail when we do the quantum 3-bit code, the analogous quantum code. Okay, but maybe you can just look at this either as, in this case, odd versus even parity, or you look at this majority voting kind of thing, and you know that if you check pairs, well, the formal way of doing this is to check pairs of bits, check their parity, and that will detect the errors for you. And once you have detected, the error correction step is very simple. It is simply to flip the bit back. So you know which is the bit that got flipped, and you just have to flip it back to the original state, right? So it's just a single bit flip. That's all the error correction step is, based on the error detection step, right? Based on the error that was detected. The final step after error correction is what is called decoding, which is the inverse of the encoding process. Literally, it's an inverse mapping, right? So you've mapped from 0, 1 to 0, 0, 0, 1, 1, 1. You've done the error correction. The error correction brings you back to the code words. right? The error correction step, it takes you back to the code words, and the decoding step is basically to map the code words back to 0 or 1. Okay, and this kind of completes the process. So any questions? Okay, so
Excuse me,
hopefully,
ma'am.
yeah.
I did not understand pairwise parity check.
Yeah, so in either case, you leave out the no error scenario, okay? So suppose I leave this out, right? Then what I do is basically look at, yeah, I mean, I can include those also. Okay, so let me quickly explain this. So you look at 0, 0. This is, so I said it's the number of ones, right? So this is even parity. 0, 1 is odd parity, right? You look at my code words, the original code words, right? If I look at any pair of bits, the 0 logical code word has even parity, and the 1 logical code word has also even parity. So the thing to note is my code words, if I go by pairwise parity, so they have even pairwise parity. Okay. Is that clear? Who asked me the question? Neelkant.
Yes, ma'am.
But now you look at your, what happens to the 3-bit strings you get after the action of the errors, right? You find that in every one of these 6 strings, you will find one pair at least will have odd parity, right? So in all these errored words, bit strings, there will be at least one pair has odd parity. Do you see that? So in this case, this one will have odd parity, the 0, 1. In this case, this pair will have odd parity. In this case, this pair will have odd parity, right? Similarly here, here, and here. Is that clear?
Yes, ma'am.
So
Yes, ma'am.
essentially, you just have to look for that. So you look at, there are 3 pairs that in each string, and you look at the parity of each of these pairs, and whichever has odd parity, that tells you the location of the error, in fact. So you will find that. So let me just try to highlight only the odd parity ones. This one, right? And in this case, it'll be this one. So that then tells you the location of the error. Okay, so if I compare parity of, if I call this as 1, 2, and 3, and I find that 2, 3 has even parity, but 1, 3 has odd parity, and 1, 2 has odd parity, then I know that the error location is basically 1. You understand?
Yes, ma'am.
And this will be a unique mapping, and you can check that, right? So whichever pair or pairs, so there can be 2 pairs that have odd parity or only 1 pair that has odd parity, whichever, whatever be the case, that will essentially tell you the location of the error. So this idea, right, that you check for something and that gives you an indication of where the error is. Okay, this is what is called a syndrome. So what you're doing with this, so this is what is called an error syndrome, right? So the key step in the error detection process is to get the error syndrome. Okay, and in the classical case, the error detection process is simply parity check, and it's a pairwise parity check of the code words that you have. Of course, if you find that there is no pair that has odd parity, then what does it mean? If none of the pairs has odd parity, or if all the pairs that you check have even parity, then
No error.
exactly. So do nothing. So that's what is the case with your code words itself, right? It means that no error. So your code words remain as they are. So there's nothing to be done. So that should also come out in your syndrome, right? That either there's been an error or it's no error. And if there has been an error, where did the error occur? All of this information has to come through in your syndrome. Okay, does that explain it?
Yes, ma'am. Yes, ma'am.
Okay, so that's what the detection step is all about. It's about getting what is called error syndromes. I just put singular here because there's only one kind of syndrome, but it could be plural, there could be multiple kinds of syndromes actually, more complicated error models as in the quantum case. And once you have detected, error correction usually is simple. You simply have to reverse what happened. In this case, it's a single bit flip. And the location of the single bit flip, where do you have to do the correction, that the syndrome will tell you, right? So based on the error detected, the more formal way of saying it is it's based on the syndrome. And finally, the error correction step will lead you back to 000 or 111, and these have to get mapped back to 01, and that's your decoding process. It's literally the inverse map of the encoding. Okay, so these are the key steps of any error correction process, whether classical or quantum, and I just wanted to show you what happens in the classical case because a lot of this analysis simply follows through in the quantum case. Now, what about these order p squared errors? So let's look at just one example of that to understand that this code cannot correct for order p squared. So 000 under a 2-bit flip could get mapped to one of these, right? It could get mapped to 011, 110, or 101. And now you notice that all of these can also, the same set of strings you get by the action of a single bit flip on 111. Correct? So the same set of strings, the action of a 2-bit flip, right, on the 000 code word gives you the same set of strings that a single flip will give you on the 111. And now you understand why you cannot correct for the 2-bit flips, because these are no longer unique. So they are no longer unique strings, right? In fact, you have exhausted all the possible unique strings that your 3-bit set can give you, with the set of single-bit errors itself, right? So there's no more room for you to have bit strings which are distinct for the 2-bit or the 3-bit errors. Okay, and this is the reason why this code cannot correct for. So the 3-bit repetition code cannot correct for, it cannot detect even the 2-bit flip errors. Why cannot it detect? Because when I check the parity of pairwise parity and so on, I'm going to map these back to the single bit flip errors. And I'm going to say that actually I'm going to map all of these back to 111. That's what the 3-bit code is tailored to do. It cannot distinguish whether the 011 came from a single bit flip on a 111 or from a 2-bit flip on a 000. So there are no unique syndromes for the 2-bit and the 3-bit errors. In fact, the 3-bit error is going to map one code word to the other. And that's pretty dangerous kind of error because you cannot even distinguish that, because both 000 and 111 are good states for you, right? They're both good bit strings. You're not going to tamper with them. But if what was a 000 became a 111 or vice versa, then that's a completely undetectable error for this code. Okay, so the 3-bit repetition code cannot detect 2-bit flip or 3-bit flip errors because there are no unique syndromes that distinguish these errors from the single bit or the no error case. Okay, and that is why the 3-bit repetition code is a single bit error correcting code. Okay, so this is often written as 3-1. I will just stop with 3-1 now. I'll explain the there's one more parameter which I should write, but we'll do that later. So you can think of this as a 3-1 code. So it encodes 1 bit in 3 and corrects for 1 bit flip errors or single bit flip errors. Okay, fine. So now the question is, can we do this? Can we sort of repeat this process in the quantum case? Okay. So what do we have to do in the, so this was just, so here I just wanted to talk about the higher order errors. That's what we did. All right. So now on to the quantum case. So let's take the same noise model. But before that, I want to say a few general things about quantum error correction, right? So the first thing you notice is that there is a whole, that it is no longer just a finite set of error models or finite set of noise channels, right? So there is a continuous parameter that means the continuous parameter families of noise maps, right? What do I mean by that? So for example, if I just look at qubits, for example, so just think about qubit noise channels. Okay, any map, which maps from the set of states on qubits to the set of states on qubits, this is the C2 space, is a valid noise channel, of course, provided it is CPTP. But you can imagine that I can construct an infinity of them. So the first question becomes, can you even think in terms of just discrete error models, right? Because you have this continuous space, right, of noise channels or noise maps. Okay, unlike the classical case where we said that you can either flip the bit or you can erase it, and that's pretty much all that can happen, right? Anything else is a dressed up version of one or both. There's nothing else that can happen, but you already saw in the quantum case that you can have a bit flip, you can have a phase flip, you can have depolarizing, you can have amplitude damping. So you think about all the examples that we did and you realize that the noise is no longer describable as easily as in the classical case, and there is not just one kind of noise, there are several kinds of noise maps. And each of them are different. So the amplitude damping, for example, is a non-unital channel, and then you have unital channels. Some of them are Pauli channels, some of them are not Pauli channels, etc. Right? So there is this continuous space of maps that one has to deal with. So that is the first challenge, right? Now, suppose I restrict my attention, even if I restrict my attention to just the bit flip noise, right? So I'm just listing out what are all the different issues. So So you can think of all the different, so you have bit flip, phase flip, amplitude damping, depolarizing, and actually I haven't discussed erasure. So there's also erasure, etc. Right? So there's all of this. The second issue, suppose you look at, so I'm just going to call this second issue as the issue with encoding. Okay. What is this issue with encoding? Do people already see what the issue is? So even if you just focus on, let's say, the bit flip noise, and we saw that it's the same kind of noise, right? So you had the same 0 going to 0 with probability 1 minus p and going to 1 with probability p, right? So you have the same kind of model. So can you do this repetition code now? So can you think of a 3-qubit? Yeah.
Ma'am, to do that, we would need to observe it and then the state would collapse, so it wouldn't work, right?
Exactly. Is there a more formal way of saying it? That of course you will have to know what the state is and it will collapse, etc. So what is the fundamental objection to doing a repetition code?
It cannot be copied.
Exactly. So you cannot copy quantum information. Even if I just look at 0, 1, right? 0, 1 might be distinguishable states. But now what do I do with alpha 0 plus beta 1? Because these states are allowed now, right? You have to deal with superpositions. And the idea that any state can now be, that you can make 3 copies of any state is simply not going to be possible, right? This process is forbidden. So this cannot happen. And this is forbidden by the no cloning theorem. So you cannot clone an arbitrary superposition of 0 and 1, right? So I don't have a way of doing the repetition code exactly the way I did it in the classical case, where every symbol was simply replaced by 3 copies of that symbol or whatever number of copies of that symbol, right? I cannot replace every state by 3 copies of itself. There is no way to copy the state. Okay. So this kind of idea is forbidden by the no cloning theorem. So the encoding has to be done in a way that bypasses the no cloning objection. So it has to somehow work around the no cloning theorem. So this is the next serious hurdle that has to be overcome, right? And the third objection, comes in the error detection part. The third challenge rather comes when you try to do error detection. What is the challenge here in the quantum case? In the classical case, we simply looked at the bits, checked parity, and decided whether there was an error, where did the error occur, etc. What is the challenge in doing that in the quantum case?
The state will collapse and we'll lose the information.
Exactly. So this is where what someone said for the previous one really holds, that measurement collapses the state. And then the entire purpose of this exercise is lost, right? So the question becomes, can we extract syndrome? And syndrome is just a fancy or a technical word for saying signature of an error, right? So can we extract information about the errors without collapsing the state or without destroying superposition in particular? Because that is where the information is. And we know from doing all these algorithms that you have to create some fancy superposition states in order for these algorithms to really work and have this nice speed up and everything. And those are the states that you really have to encode. And those are the states on which you are going to somehow do error detection and error correction. So can you extract error syndrome without destroying superposition? So this is the third challenge. So there are three main issues that have to be overcome in adapting the techniques of classical error correction to quantum error correction. The beauty of it is that this is still possible, right? It is still possible to work out a cogent theory of quantum error correction which can overcome all these objections, right? So the first, so let's look at the, so I like to call this quantum tricks. So this is from a little limerick or a poem that was written by Daniel Gottesman, who was one of the pioneers of quantum error correction. So I will refer you to this poem at some point. It's a cute little limerick that tells you also, I mean, once we do stabilizers and everything, it'll become more clear what that little poem means. But what he says is we need new quantum fixes or quantum tricks to resolve these issues, right? And what are these quantum tricks? So the first one, the way I have written it down, the first one is about continuous to discrete error models. So now we said that there is this whole, this whole space of error maps, right? The point is the mathematical structure of these operators, that itself provides us a solution also. And what is that solution? So if I focus my attention on just the qubit errors, right, which is maps from the state space of single qubits to the states on single qubits, you know that any such CPTP map has a set of Krauss operators. Now the problem is that this set of Krauss operators could be arbitrary, right? However, these are all 2 cross 2 matrices, correct? In the case of qubits, these are all 2 cross 2 matrices. So is there a way to represent all 2 cross 2 matrices in terms of some small discrete set? Yes?
It's
Is
a
there a way to
Pauli
represent?
operators form a basis. So we can-
Exactly. So now, since the Krauss operators are all 2 cross 2 matrices, each of these Krauss operators I can expand in terms of some C0 I identity plus C1 I sigma X, I'll just call it X, C2 I sigma Y, C3 Z. So I can express all of them, so I can discretize in terms of the Pauli basis. And this has multiple advantages because the Paulis are, of course, a nice set of operators. And if I am able to develop a linear theory of error correction, then it will suffice if I correct for X and Z errors. Because every error, this is an arbitrary error, right? When I write an EI, it's an arbitrary error, can be broken down or decomposed in terms of a linear combination of x, y, and z errors. Why does it suffice to correct for x and z? Because y is simply x and z, right? So there's x, there is z, and then there is the product x times z. That's what y is. So an arbitrary error can always be decomposed in terms of the Pauli's, and similarly in higher dimensions, all that one has to do is to look for a nice error basis, right? The second advantage of the Pauli's is that they are unitary operators. So in fact, this is a unitary basis of errors in which you're decomposing every error map. So this continuous space of errors can now be visualized in terms of a discrete set. And in the case of qubits, this discrete set is very nice. It is simply the set of Pauli operators. Okay, so this is the first fix. Now, as a little homework, what you can do is to look at the amplitude damping channel. Remember, it had these two non-trivial Krauss operators. Decompose them in terms of Pauli's. So how does the amplitude damping channel look in the Pauli basis? So that is the homework for you. So what is E naught in terms of identity X, Y, and Z? And what is E1, right, in terms of identity X, Y, and Z? So this is the first tool that we have at our disposal, that because these live in operator spaces, right? Essentially, the set of all D cross D matrices forms a vector space. So any arbitrary error on a D-dimensional system can be decomposed in terms of some error basis. And then, of course, this is still relying on the assumption that I somehow am able to develop a linear theory of error correction. And we'll discuss what that means in maybe tomorrow's lecture itself. Then this problem is taken care of, because once I correct for the error basis, I have corrected for any arbitrary error. Okay. Now the second objection or the second challenge in going from the classical to the quantum is the encoding issue, and that somehow you have to overcome the no cloning theorem. So how does the encoding process? You need to encode despite the no cloning theorem. And the tool that helps us to do this is essentially entanglement. Because if you think about it, entanglement provides us a way to look at multi-qubit systems. That's what you need to do, right? You have to go from single qubit to multi-qubit. But if you now construct a correlated multi-qubit state, then that is a way of introducing redundancy which does not violate no cloning. So let us look at a concrete example of this, and then we see how this can be done. So you consider this alpha 0 plus beta 1, for example. So the example will be the quantum. How will you do a quantum 3-bit code? So let me say 3-qubit error correcting code. So what cannot be done is 3 copies of this, right? So this tensor 3 cannot be done. But what can be done is a superposition of a 3-qubit 0 and a 3-qubit 1. How can this be done? So you imagine that you now have, so you need 2 additional qubits, right? Obviously. So you have to go from a single qubit space to a 3 qubit space. So you need these 2 additional qubits. So here's a circuit that will do this for you. This is the first qubit. The first register is often called the data register or the data qubit, similar to what we have discussed in various algorithms, right? And these are now ancillary systems. And how can we achieve this kind of a state? Yes, how do we entangle qubits?
C0 gates.
Exactly. So we have to apply C0s. Good. So indeed, that's all there is to it. You just apply 2 C0s, right? Both of them with the first or the data qubit as the control. And in one case, the second qubit is a target. In the other case, the third qubit is a target. And that's it, right? So I leave it for you to check that now the output state is actually of this form. And I hope you realize that this is actually an entangled state of 3 qubits. If alpha and beta were 1 over square root 2, this is a special kind of state. It's called the GHZ state. Right? It's a max. If alpha and beta were 1 over root 2, then it would be a one of the maximally entangled states in the 3 qubit space. Right? So now you have done, essentially what I've shown you is a encoding circuit, right? And of course, because this is just comprising of 2 C0s, this whole process is unitary. So this is a unitary encoding circuit. I mean, the very fact that I have a quantum circuit means that the process is unitary, because the circuit can only have unitary gates, right? And this is exactly what an encoding map should be. It should be invertible. That's what we said in the classical case, right? You need a way. Suppose I finally get back to the 0, 0, 0 and the 1, 1, 1. I need a way to map back to the single qubit, right? And that is possible only if the encoding itself is unitary. Then the decoding is simply the inverse operation of this, right? So we have now both circumvented the no cloning theorem using entanglement. And what is more, we have shown that it is possible to have these kind of nice encoding circuits, which are essentially unitary operations. They are unitary operations on a larger space. Okay, so let me, now is a good place to stop and define what one means by a quantum code. So what have we done here? So we have gone from a single qubit space. This is the C2, right? To 2 states of the 3 qubit space. You see, the 3 qubit space, so let me write that here, is a much larger space, right? The 3 qubit space is C2 tensor, C2 tensor, C2. So what is the dimension of this space? What is the dimension of the 3 qubit space?
Eight.
Yeah, this is 2 cube or 8. But what we need is only a two-dimensional subspace of this 3 qubit space. Because so essentially what was 0 has become 0, 0, 0. What was 1 has become 1, 1, 1. These are the 2 new basis states that we work with. And all the action is happening in the span of this 0, 0, 0 and 1, 1, 1, right? So we only need to go from this physical space to, now I'm going to put the 3 zeros in a single ket. It means the same thing. This is the so-called logical space, and 0, 0, 0 and 1, 1, 1 are the code words or the logical states. So they are the logical 0 and the logical 1. I'm encoding only 2-dimension worth of information. A space which is 2-dimension is what has to be encoded. So what I need is only a 2-dimensional subspace of the 8-dimensional space. So this logical space is only 2-dimensional, just like how the physical space is 2-dimensional. So a quantum code is therefore a subspace of a larger Hilbert space, right? So I can define this more formally, and maybe I'll do that in a lecture or two. But again, there's a departure from the classical case where you simply have gone from a single binary field to like multiple copies of this field, right? And then all your strings are distinct and so on. So there's no notion of a subspace. There's no vector space idea coming in there. But now here we have this notion of a subspace of a larger Hilbert space coming in. So in this particular case, we have gone from C2 to a 2-dimensional subspace of C2 tensor 3. So I often draw a cartoon picture of this. So if I think of this somehow as my original space, this is now encoded inside some larger Hilbert space, and this larger Hilbert space is now the 3-qubit space. But I'm only looking at one 2-dimensional subspace of this larger Hilbert space, and this is the subspace. It's two-dimensional means it has a basis with just 2 orthogonal states, right? And these 2 orthogonal states are exactly my logical 0 and the logical 1, right? And that's what this 2-dimensional space is. It's a span of this 0, 0, 0 and 1, 1, 1. And I've shown you how I can achieve this encoding. I can embed this 2-dimensional space in this larger space by attaching ancillas and implementing a unitary quantum circuit comprising just of a pair of C-naughts, right? Questions? So this is the crucial part to understand the structure of the error correcting code, that it is a subspace of a larger Hilbert space. Your physical space has now expanded to n qubits in general. In this case, it is expanded to 3 qubits, but you are only accessing a small subspace of this n qubit space. Usually it's just and as a qubit, right? So I'm encoding a single qubit. So that means it's essentially a 2-dimensional subspace of a larger 2 to the n dimensional space. In this case, it's a 2 to the 3-dimensional space. Okay, so the final challenge was error detection and how to get syndrome by quantum measurements, right? How to overcome the collapse issue. So again, the fix. So if you look at it, how did we fix the problem here? We appended a pair of ancillas, right? Once we attach a pair of ancillas, then it kind of became clear that we had to do C-naughts, and that's how you would introduce redundancy in some way, right? Essentially, what you're doing is you're picking a correlated part of the Hilbert space to store the information in. So you're going to a larger Hilbert space, and then you're identifying a nice subspace of this larger space in which you can store the information in. How do you circumvent the collapse? Well, the same way. So use ancillas again and measure only the ancillas, not the data qubits. Right? So if I do not measure the data qubits, then there is no danger of collapsing them. Right? So you measure only the ancillas, don't measure your data qubits. So here again, I'll just draw the circuit, and tomorrow we'll discuss the 3-qubit quantum code in greater detail, because I haven't even told you how the error maps these code words, what kind of states does it map to, are they distinct, etc. All that we have to discuss. But I'll just show this picture here that I have my I have these 3 qubits now. So think of the 3-qubit code, right? I have 3 data qubits now. I started with a single data qubit. After the encoding, I have 3 data qubits. So the way to now do the error detection is to introduce 2 ancilla qubits. Once again, how do you extract the information from the data to the ancilla? What would you do? You have to find a way of entangling the data qubits and the ancilla qubits, right? So once again, this happens via C-naughts. So here it is. So in fact, this is an exact error detection circuit for the 3-qubit code. I have to do 2 C-naughts. So if I call these data qubits as 1, 2, and 3, the first ancilla has 2 C-naughts with both data qubit 1 and 2 as control. And the second ancilla qubit has 2 C-naughts with the data qubits 2 and 3 as control. And that's about it. These are all unitary operations. So you do not end up affecting the data qubits. The superposition is not destroyed. Whatever information they were carrying, they continue to carry, right? So after doing these C-naughts, I simply measure these 2 ancilla qubits. And this gives me some set of classical bits. Oops. This gives me another classical bit. And these classical bits constitute my error syndrome. Okay. So I'll stop here and we'll resume tomorrow. And in fact, we'll discuss how all of this helps us to actually correct for single qubit bit flips. But I hope this has convinced you that by not doing anything to the data qubits and just by attaching ancilla qubits and measuring them, we have overcome the collapse problem. So these remain in whatever superposition they were prepared in, they continue to remain in that superposition, right? So we are not actively destroying that superposition by doing measurements. Okay. All right. Stop here. Any questions? Okay, there are no questions. Then we'll meet tomorrow at 3:25.